speaker, but I will take questions if we have time, Gene.
Yes, thank you very much. We have time for one or two questions. Yes.
Quick question about sensors that you mentioned. What types of sensors are you focusing on there?
I mean, that's a great question. Given the breadth of the work that we look at in water resources, I'm not picking a flavor. It's how is it, either from a quantity side or a quality side, can we come up with a couple core standards? And some standards already exist. There's a sensor observation standard. There's the object and model, observation and results, measurements standard. So it becomes a chaining of standards, and which, again, standards, data model, kind of think along those lines.
Yes, Tom.
Has your group looked at it from a problem standpoint? What I'm talking about is both EPA and NRC and other government agencies worry about leaks from their facilities. It could be an underground tank controlling chemicals or radionuclides, whatever. Do you look at it from the standpoint of how do we create standards for these sensors to detect leaks? And then how could that data be used to look at water quality, especially groundwater? And it could be in the unsaturated or saturated zones.
I wasn't planning on going into that level of detail for this report. I know there is a whole group within EPA, within ORD and the FEM working on sensors and how do we innovate around sensor-derived information, but I'm not up to speed on that. I think one of the challenges, though, when you take that more focused approach where you go for a industry, is you're diluting the marketplace for the public or for the private sector that wants to build technology. They don't want to build niche specific standards. They would like to see a standard that they can sell to a wastewater industry and next time take it over to Dow Chemical. And that's not on what the censoring capability is, that's on what the package of information that gets transmitted out is.
Thank you very much, Todd.
Oh, good morning. I'm Bruce Hamilton from the National Science Foundation, and I'm going to introduce the final speaker before the break, and that's John Goodall, who's a professor in the Department of Civil and Environmental Engineering at the University of South Carolina. And much of, a good portion of his research is on the topic of his presentation, which is the Kawasi Hydrologic Information System, HydroServer, HydroCatalog, and HydroDesktop. You've heard a little bit about Kawasi. Kawasi is a consortium that is supported by the National Science Foundation. It has well over 100 members, university members, so it's quite an extensive organization that has been running for a number of years. And one aspect of that is the hydrologic information system that John will tell you about. So, John?
Okay, thanks, Bruce. It's nice to be here, and it's nice to talk behind these two excellent speakers because you've already explained a lot of the concepts I have to explain normally when I give this talk. We heard about standards and components, defined Quasi already, and Bruce did a great job explaining what Quasi is, so let me just head into it here. So here's my slide on what Quasi is. We have about 125 university members, and among other things, one of the goals of Quasi is to develop and support operating research infrastructure for the hydrologic science community. And another aim of Quasi is to improve data access, so access to information and access to models, and that's what I'll be focusing on here today. We are supported by NSF. This is a large project team. I'm one of the co-PIs on the project. David Mayman at the University of Texas at Austin is the principal investigator. And we have folks at Utah State, San Diego Supercomputing Center, and Idaho State. Oh, before I move on, all the information that I'm going to be talking about here and a lot more additional information is available on our website, his.quasi.org. All right, so the problem statement. So there's a growing amount of data that's becoming available to do science with. Remote sensing, sensor networks, model output. How do we handle and make use of that information to advance hydrologic science? That's really kind of the problem statement that we're trying to address. And one of the things we're focusing on this particular project, this quasi-HIS project, is facilitating user access to this information. And it's really a scientific goal of testing hypotheses and doing analysis. And the way the system is set up is it's a distributed system, meaning that we keep the data with the data producers. So we don't create one gigantic database. We create mechanisms that allow us to go and query the data on the fly. And so within the network, within the quasi-network, quasi-HIS network, we might have a lot of different types of information. So information from university investigators. So you're doing an experimental watershed in a particular part of the country. You could set up a database and load your information into it, and it can become accessible through the system. We've also partnered with some federal agencies and done our own kind of prototyping and coding to try to make these federal databases that are relevant to the hydrologic science community available through the system. And then some state level data as well. So especially in Texas with David Mayman's influence, a lot of their information is available through this system. The way the system is architected, it's much like the internet works in general. So we have these Hydra servers. I'll talk more about each one of these boxes and slides coming up, but essentially the servers are where the data is stored. We have something called HIS Central, which is our metadata catalog. And what this is doing is it's going through and looking at all the different servers that are out there on the web and kind of crawling them, finding out what metadata is available, what information is available in them, and creating a metadata catalog. So again, we don't get all of the data. We just get the information that would be relevant for searching and finding information. And then there could be multiple client applications that use this system. We're developing something called Hydra Desktop, which is a GIS-based interface, and I'll show what that looks like in a moment. But this would be the primary user interface for people that want to use the system. So if you're not into all the geeky stuff and you just want to find data, you would open up this desktop application, zoom into where you want to do a study, and put in some keywords. I'm looking for nitrogen data. It will go search over the web of all the different servers are out there. You find which information is relevant to you, and it will download it, essentially. So from the end user perspective, that's how it would work. So one of the first things we did on the project, this is work being led at Utah State University, is to develop a database model for observational data. And this is called the Observation Data Model, ODM. And so the idea here is you have sensors. Again, academic researchers will have sensors within their experimental watersheds that are collecting observations. How do you streamline that process of getting those sensors into a database? Once it's in that database, we have what we call the Water OneFlow web services, which are essentially a set of functions that a computer program can call to access information. So one of the functions, for example, is get sites. And get sites will tell you what sites are available within that database. All right, so these aren't really intended for a human to use, but this is what the software, the Hydra Desktop software, goes and calls these different functions to figure out what information is within that database. So for some databases, so for example, the National Water Information System that USGS maintains, of course they have their own database, and we're not going to influence what type of database they use. But they can and they have put on this Water OneFlow web service interface. So the back-end database can be whatever you want. As long as you have the standardized interface, it can be accessible through the system. And the data gets transmitted over the web with this WaterML language that Todd talked about earlier. This is a standard that we developed through this project that's now gotten some legs with OGC and is being morphed into WaterMel 2.0, which will be an OGC standard. So another view here of the way that the system works. So it's when you try to integrate systems, it's really about the interfaces. I mean, that's what's so critical to get right. And so we have this Water One flow, which is really a set of query functions for each service that lives out there on the web that's part of this network. And they return data in this WaterML format, which is an XML format. If you're familiar with XML, you can open it up with a text editor and look at it. But again, it's really intended for a machine to parse out information very quickly and efficiently, self-describing a lot of the metadata that's included within that WaterML document. One of the big challenges that we faced, of course, is semantic mediation. We have information in here from different federal providers, from university folks and everyone, of course, uses their own terminology, slight differences that mean the same concept. Are we talking about the river height or the river stage? So that if you don't be very specific about what you mean, the computer is going to choke and not find the information you want. So we have to go in and have these ontologies essentially that allow you to map similar keywords to the same overarching concept. And so a lot of the work is really trying to, now that you have this whole this distributed data system and you're not really restricting each of the data providers to do things a certain way, you have to have this essentially middleware that does a lot of translation for you. In the bottom of this slide too, this is somewhat out of date here, but within the system, we have 66 different services, so 66 different databases, if you will, that live out there on the internet. 18,000 variables, 1.9 million sites, and 29 million series, so these are time series, and 5.1 million individual data values, and it's growing. So as people go and set up a Hydra server and register it with the catalog, it will go and index it. So this can grow to be as large as, you know, it has no real limit in terms of how large this thing could grow. Hydra Desktop is, again, I mentioned the primary user interface for the application. This is built off an open source GIS platform that's being developed at Idaho State University called MapWindow. It's got a familiar GIS interface to it, and it has a keyword kind of search wizard that will allow you to find information that's distributed within the HIS, go and locate information for a particular place, download it, and it downloads it locally into a database. It's built as a system that is extensible, so you can have additional plugins. So one of the things my group has been doing, and this builds off the OpenMI that Peter talked about, we're interested in modeling and how you would do modeling within this kind of context of the HIS. And so when we think about modeling, we think about it more as a set of tools in a toolbox. And we're really interested in this OpenMI idea providing a mechanism for integrating the tools. So you might think of a tool set that a hydrologist might need to do some analysis consisting of hundreds of different little components that do different process routines. And what we've done is created relatively simple readers and writers that can go and get the data out of the HIS, feed them into these models, and then take the results from a model, write them back to the database. So within this one environment, you can kind of visualize your input, your output, build up these models to create new information, visualize it, and try to be a very highly interactive environment for both research and for educational purposes. So Peter already talked about the OpenMI. I'll just briefly mention it. So the main idea here is how you couple models together and being very explicit about what information is being passed between the models, where is that information relevant, what exactly is it, when was it measured. And OpenMI, I think it's safe to say, was really developed for wrapping large legacy models or existing models. We've taken a slightly different approach.